Hello everyone. So this is the second lecture on the chapter magnetism, and we will see torque. Today we will see torque on acting on a magnetic dipole. When you place that in a magnetic field, then work done in rotating a dipole against the magnetic field, and then potential energy and some more topics. So firstly, you can see on the screen the diagram. In the diagram, you see the blue lines are representing the magnetic field which is going from left to right. Okay, the magnetic field is going from left to right. The blue lines are representing that. Now you have a dipole of length twice L, and it is making an angle theta with the field. Okay, so the north of the dipole is along the field, and the south is like naturally it will be opposite to the field. Therefore, a magnetic force plus MB will act. The plus minus is not shown over here. However, a magnetic force plus MB will act on the north pole towards the field, and a minus MB magnetic force will act on the south pole against the field. The perpendicular distance between these two forces is, if this is twice L, if this is theta, then this will be twice L sine theta. Okay. So what is the relation for torque? Torque is equal to force, either force into perpendicular distance between the forces. So either force like MB into what is the perpendicular distance between the force, that is twice L sine theta. Now M into twice L you can write down as capital M, which is the magnetic dipole moment, B sine theta. Now in vector form you can write this as M cross B. Okay, so this is the scalar relation, and this is the vector relation. So this is your relation for torque. The unit is Newton meter. Okay, force and distance. Force is Newton and distance is meter. Now, torque on which alignments, like this is not of course included in the PDF. However, this is pretty simple, and everyone should understand. Now, if this bar magnet is lying along the field, like north is here and south is here, then you will say that theta is 0 degree. In such a case, if theta equal to 0 degree, then you see tau equals to mb sine 0 is 0. That means no torque acts on the bar magnet, even if theta equal to 180 degree. So 180 degree also, in that case the bar magnet will lie like this, but north will be here, now south will be here. This is like this situation you call as anti-parallel. Okay, bar magnet is lying anti-parallel. In that case also no torque will act on the bar magnet. But there can be a third situation, like the bar magnet is like this, north is here and south is here. This can be the third situation, and the fourth situation can be north is here and south is here. Okay, we have a diagram a little while later. You will understand this there also. So if theta equal to 90 degree, if theta equal to 90 degree, 90 degree sine 90 is 1. So tau equals to mb. Now maximum torque will act on the dipole when it is lying 90 degree with the magnetic field, and if theta equal to 270 degree, then tau equals to minus mb. Okay, so this will be the value for the torque for various angles of theta. Next we come to work done in rotating a dipole. Now you see in this diagram you have this dipole, the north of the dipole is this, the south is this. Now it is again making certain alignment with the magnetic field. Now if you want to do work, then you will just rotate it. You will try to rotate it against the field, right? Because naturally it will have a tendency to rotate along the field. Now to give a small displacement d theta, okay, the small amount of work done will be tau d theta, right? So tau value is mb sine theta d theta. So this is the value for dw. Now if you want to rotate this dipole from some initial angle theta 1 to some final angle theta 2, right, then the total amount of work done in the process will be integral of dw over the limits theta 1 to theta 2, right? If you get the value of dw, then integral of mb sine theta 1 to theta 2 d theta. Now magnetic dipole moment of the given magnet will be constant, right, and it is a uniform magnetic field, therefore you have b constant. So integral sine theta d theta, theta 1 to theta 2. So what is integral of sine theta? That is minus cos theta, right? So this gives you minus cos theta, theta 1 to theta 2. Okay, and therefore your relation comes out to be, now since there is a negative sign, we will be doing lower limit minus upper limit. Clear? So this is your relation for work done. Work done relation is mb cos theta 1 minus cos theta 2. Now potential energy of the magnetic dipole. Okay, next we have potential energy of the magnetic dipole. Now how do you define this potential energy? Now if you rotate the dipole, if you rotate the dipole from a direction lying perpendicular to the magnetic field, right? That means in this situation what will happen, maximum torque will be acting on the dipole along the field, right? So you will also require maximum counter torque to rotate it against the field. Clear? So you are rotating it from an initial angle 90 degrees to some final angle theta. Clear? So theta 1 value will be 90 degree in this particular relation, in this work done relation. Theta 1 value will be 90 degree and theta 2 value will be theta, some final angle. So that is what you call as potential energy of the dipole. Now theta 1 90 and theta 2 theta, if you place it in W, MB cos 90 minus cos theta, this gives you minus MB cos theta. Now this work done will store in the dipole as potential energy of the dipole, and therefore U, the scalar relation, is U equal to minus MB cos theta. In vector form you can write down minus M vector dot B vector. So this is the other relation for potential energy. Now we have special cases. If you place in this relation, okay, if you use theta equal to 0 degree, then U equal to minus MB, because 0 is 1, right? So minus MB, this will be the minimum value of the potential energy. Now you know one thing, that when potential energy is minimum, the tendency to change from that position will be least. Okay. Now situation number 2, when theta equal to 90 degree or 270 degree, we are considering two situations in one point itself. In diagram we'll put it separately. Now when like cos 90 in this relation, cos 90 is 0, cos 270 is also 0. So in this position your potential energy will be 0. Okay, I'm writing it here, U equal to 0. This is the intermediate value, not the minimum. The minimum is negative, minus MB. And if theta equal to 180 degree, now the bar magnet will lie anti-parallel to the magnetic field. Okay, in that situation your U comes out to be, now cos 180 is minus 1, therefore the relation will come out to be plus MB, and this is the maximum potential energy of the dipole. So in this situation it will have maximum tendency to change the alignment. Now if you see that in the diagram, yes, these are the diagrams. Now in case 1, you see here theta value is 0, since north is lying along the field, south is lying opposite to the field. So in this alignment the potential energy comes out to be minus MB. For cos 0 it is 1, and therefore minus MB cos 0 degree will give you minus MB. So here potential energy is minimum, it will not have any tendency to change from this position. Okay, here no torque is acting because MB sin theta, MB sin 0 is 0. So torque acting on the dipole in this alignment, like when the dipole is parallel to the magnetic field, torque acting is 0. So you call this situation to be stable equilibrium. Okay, stability is there and this is an equilibrium condition. Now you see diagram number 2. Now you twist it anti-clockwise direction by 90 degree. Okay, so in that case maximum torque will act, sin 90 is 1, so MB sin 90 will get you MB. So maximum torque will act on this, this dipole in this alignment, and potential energy will be 0 here. Okay, mind it, this is not minimum, 0 is not minimum, minus MB is minimum. So potential energy is 0 in this arrangement, potential energy is also 0 in this arrangement. Okay, so here it is like theta equal to 90 degree, here theta equal to 270 degree. For 270 degree, north has come down, you see. Here north was here, this is 90 degree, this is 180 degree, and this is 270 degree. Okay, so here potential energy is 0 and torque is minus MB. So maximum again, but in the opposite direction in comparison to this. Now case number 3, here theta is 180 degrees. So you call this condition to be anti-parallel because north is lying opposite to the field. The field is along the right and north is lying opposite, and south is lying towards the field. Now in this arrangement it will have maximum tendency to deviate or to change this position. So you call this condition to be unstable equilibrium. Okay, unstable. This is not a stable configuration or arrangement. Here torque acting is 0 because sin 180 is 0 again. So I hope these 4 diagrams are clear. So after this we have magnetic field lines. So what are magnetic field lines? Now these are imaginary lines. Okay, so magnetic field lines you can see in this here there is a bar magnet at the center, right? So this is a bar magnet. Now here from the bar magnet, these are the magnetic field lines. The magnetic field lines are imaginary lines. Now if you draw a tangent at any point on a magnetic field line, right, the tangent will show you the direction of the magnetic field at that particular direction, sorry, at that particular instant. Okay, so now properties. What are the properties of magnetic field lines? Now from the north pole, here this is the north pole of the, well, north pole, it is written there only. So from the north pole, this side is north pole. From the north pole, field lines go from, or you can say outside the bar magnet, field lines go from north to south. Inside the bar magnet, it goes from south to north. Okay, so that is point number one. Point number two, unlike electric field lines, now you see magnetic field lines, they form closed loops. This is not the case with electric field lines. Okay, if you remember. Now point number three is tangent. Now that point we have already covered. Like if you draw a tangent at any instant, what do you understand? What you get is the instantaneous magnetic field direction. Okay, now these field lines never cross each other. They will not intersect each other. Here you look at this, you cannot have a situation where one field line is intersecting with the other field line. In that situation, if you draw a tangent at the common point, you will have two tangents, right, representing two different directions for the same magnetic field, which is not possible. And that is the reason magnetic field lines or even electric field lines do not intersect with each other. Okay, so next point is number of field lines is directly proportional to the pole strength. So more the number of field lines, okay, near a pole, greater the number of field lines, greater will be the pole strength. The pole is located somewhere inside the end. Clear? So these are the pole locations. Next is number of field lines per unit area. So you take one area here, you take one area here. Okay, same area, 1 centimeter square. So if the number of field lines is more, wherever the number of field lines is more, there the magnitude of the magnetic field will be more. Okay, so this is the fourth point. And the last point is, now you see here like poles, we are placing two north poles facing each other, and therefore they'll tend to repel each other. Now they will create a zone in between, somewhere in between, okay, where the magnetic field will be zero. So magnetic field lines do not exist in zero magnetic field, in, or you can see in where the resultant magnetic field is zero. So this is the region. So this region you call it as neutral point. We'll come back to this later on again, okay, after seeing Earth's magnetic field. Now there are some analogy placed, okay, some analogy between electric and magnetic dipoles, okay, and these are presented in a very simple manner. If you go through them, I hope you'll understand. In case you do not, then text me, okay, I'll respond. I'll close this video here. The tangent law and the other topics, I'll include that in the third video. Thank you.